introduce the next speakers from USNA, Paul Miller and Matt Hamlet. They are going to do, well, I don't know how to divide it, but they are going to have a big show presenting us the big improvements of the USNA robot. And I have to say at that moment we don't know who's going to give the second talk because we don't have the speakers for the second talk. So it may be that you will have the talk twice. I don't know for sure yet. Paul, Matt, you guys.
I guess I can give that derivation of the Aries stress function talk I did in school every year that puts everyone to sleep.
But as a second, please.
As a second one. So I'm Paul Miller. I think virtually everybody in here has met me at some point. And over here we have Lieutenant J.G. Matt Hamlet. And in the back there is Ensign Jeff Rossman. Jeff was one of the 3 people on our team, students this year on the team. All the 3 students this year on the team were naval architects. And without any systems engineers, we had to dig deep. And we found Matt to come back for another year. And really, Matt's been the savior of the program because as motivated as students are, sometimes the expertise, Matt has been on the team since 2009, really gets the systems working. So what we're going to talk about today is a whole series of small improvements we've made to our SailBots over the last year. Many times the continuous improvement process works better than just trying to hit a big home run each time. And our program is different from just about every other one at the Naval Academy. While we do the same thing, the project is entirely for the senior class. Students just in their last year. What we do is instead of starting entirely from scratch each year, we try to build on the previous year. The students start with the previous year's boat, improve it based on the recommendations from the team from the previous year, and then use that as their baseline to start the following year's project. So we've seen some growth. We're on boat number 5 right now. The pictures at the bottom, don't worry about the clarity yet, we'll see better pictures later. We started this whole project back actually in 2007 designing a boat, and we built that boat in 2008. The first 3 boats, first time loose cannon and gilded boat, are all designed specifically for racing in SailBot, which means that maximum wind speed of 15 knots, maximum wave height of about a foot, maximum distance about 6 miles. So they're really an inshore, light air, high performance racing boat. The downside to that is pretty obvious when you say compete in Portugal. And you can have big waves and the boat just doesn't perform very well, it gets overpowered. Well, we also said, the group in 2000, who started the class in 2010 said, hey, let's look at a transatlantic boat. So our last 2 boats have been optimized a bit more toward transatlantic boats. Now this is going to be mostly a naval architecture talk for me, and Matt's going to talk about the systems engineering. So all those naval architects in the room, raise your hand. Okay, so only Jeff will be allowed to ask questions. Okay, the first thing we did was we had a student who was really interested in improving the hydrodynamics of gilded boat's keel. And on the left side here is the old keel for gilded boat. That was made out of 17-4 stainless steel, and we cast the bulb out of epoxy and lead shot, which was something you could do cold and no fumes and all very safe. As long as you don't chew on it, you're fine. But what he really wanted to do was look at titanium. And we've been wondering, since the Russians have been scrapping a lot of titanium submarines, how the cost differential would be between titanium and stainless, because the corrosion resistance of titanium in the marine environment is much better than even the 17-4 precipitation hardened stainless that we used. Well, as it turned out, we spent only $50 more making the titanium keel than we did making the stainless steel keel. So the cost effect was much better actually with the titanium. We didn't have to heat treat it, the machining cost was slightly less, so you pay up more upfront for the raw materials, in this case about 50% more, but we ended up with a much better keel, and you can see it out there. It's a much smoother surface, and there's no corrosion hitting on it after quite a while. It also reduced the weight and increased the stiffness. This is a plot from a towing tank. We have a 380-foot towing tank in our facility, and to really test the change in the keel performance, we just said, let's test it full scale. So we hooked up the boat to the towing carriage, and we ran it at various speeds. And what was interesting was, well, low speeds, virtually no difference. The wetted surface area was only a tiny bit less. But as the speed increased, the performance of the new keel showed up, and we eventually saw at the top end of the boat range about a 5.3% resistance and drag. That equates to, actually, it doesn't seem like a lot, but if we were racing, say, 8 hours, that's worth almost 15 to 20 minutes to muster around that course. So it's actually a significant amount of reduced resistance. The next thing we did was change how the light air sail was. We felt that gill the boat was a little heavy, and although she weighs around 22 kilos, but we felt she was a little heavy, so we wanted to either increase the sail area to improve her light air performance, or decrease the weight, and we did both. On improving the sail area, one of the small changes we made, this is the boat as you kind of see her today. The forestay columns all the way down and connects near the bow. The new system for the light air sail, the forestays actually connects back here, and the jib goes all the way to the bow. That theoretically reduced the yaw moment on the servo. We should have seen reduced servo loads, but we actually didn't. It was sort of lost in the noise. But the boat was clearly faster with that rig, so it seemed like a good improvement. Back in August last year, we said, we're ready to do a trans-Chesapeake. The Chesapeake Bay is the largest estuary in the United States. It's about 160 miles long. We're 120 miles from the ocean. And where we are, it's about 10 miles across from Annapolis to the other side and back. And the reputation of the Chesapeake Bay was light air, somewhat fluky, a lot of shipping traffic. So in August we said, time to do this trans-Chesapeake. So for something like 11 consecutive weekends, Matt, myself, and one or two students would go out there and attempt this thing. And I think the first 9 attempts ended with no wind after some point in time. Sometimes we got there nothing. Sometimes it would last even a couple hours. Then one day in late October, early November, we got down there and it was really windy and it was really cold and it was somewhat miserable. So it was perfect conditions to try. And off we went. Small video here on the left on the way out. See if this works now. Of course. Oh, there we go. We should have it. You see that? Okay. This is about 20 minutes into the sail. You can kind of see the conditions. Chesapeake Bay has no distinguishing geographic features on the far side. But you can kind of see her bouncing around on the waves. One of the unfortunate things was that the boat we were chasing with was relatively bouncy and wet itself. So we got all the way across. On the way back, so there we go. On the way back, we were about to test our collision avoidance system. There. This tug and barge was heading out to sea. You can see the edge of the channel marker. Gill the boat cruising along. Things looked like it was going to be a problem. And then we said, is she going to make it? Is she not? Is she going to make it? And we said, oh, we got to park her for a second. So we parked her for a second, and then the tug stopped. And we continued on. So it was kind of an interesting day. With those changes to gill the boat, we actually made one more change, which was done just before we shipped the boat. We removed all the final instruments from the mast, and we've moved them back to an antenna mast. And that turned out to be a great idea, is to get as much off the mast as possible. They gave us more stability, reduced windage up high, but actually the biggest benefit was really allowing the boat to be tested without the mast on. You could do all of the sort of cart tests in the parking lot, moving it around with the instruments up, without having to worry about putting the mast up. So that was a big success. Our main focus this last year was on the 2 transatlantic boats. One was building the boat that Jeff and his 2 classmates designed, and the second one was working on Spirit of Annapolis. Was anybody at SailBot in 2011? Well, she got the name the Gray Beast or something like this, or the Gray Whale, I think. A much heavier boat, twice the displacement of gill the boat, same length, fits the SailBot rule, but very slow. And also, she had a different problem, which was directional stability. So we wanted to cure the speed and the directional stability problems. There we go. The best way to do that, now the criteria we had was to go across the Atlantic. There's a lot of junk out there. And we wanted to make sure, we had this problem with previous boats, that if you caught weed on these vertical keels, you essentially stopped the boat. And bouncing the waves, you could actually wrap weed around the keel, and then basically the voyage is over. No one's going to clean it off. So our #1 criteria for the keel, apart from keeping the boat upright, was to shed weeds and plastic bags and jellyfish or whatever. So to do that, we'd done some testing a few years earlier, and we found that we needed a 30-degree sweep to the keel in order to really shed things. So we put that in. The second thing was to reduce power consumption of the rudder. we wanted to not move the rudder as much, so we wanted directional stability. And to do that, we wanted a fairly big, it's called yaw moment of inertia, area of against the vertical axis. So we launched Spirit of Annapolis, and there's two things we noticed right away. She didn't catch any weed, and she didn't turn at all. So she wouldn't tack, she wouldn't basically jibe, she just would go in a straight line. And she was reasonably good at going in a straight line. But we felt, well, tacking was kind of important, and jibing was kind of important. So we decided the best way to do that was start removing area from the keel and allow that yaw moment to improve. We also moved the rudder out. So the solutions here, we got reduced wetted surface areas, great, lowered the drag, reduced resistance to turning. We ended up also, because we changed the keel planform area in its center, we had to move the mast step. We also removed weight at the same time out of that keel, which was a plywood keel. And so we had to move the bulb. And we made the rudder post vertical. So next slide shows that development. Here we've got the original keel. Huge, huge rudder. And yep, it guaranteed to go in a straight line. Also not to turn. So what we did was, first thing, we took the rudder out and we moved it back and we made it vertical. We took a piece of the keel we cut out and put a skeg on it, so it protected it and actually reduced the power consumption a little bit by doing it that way. And then we cut all this area out, we swept the keel back, and we added a couple of plies of fiberglass in order to make that stronger. So that boat is actually going quite well. We'll see a short video here in a second. Based on this, the Spirit of Annapolis changes, the underbody for the new boat, called Waiting to Happen, is there. And we went even further. We used carbon this time to make the keel. We also carved the foam into an airfoil shape. The inspiration for that, coincidentally, was the Flying 15, which if you go into the boat park, you'll see, I think, 14 examples of it. It was designed by Alpha Fox a while ago. And they're interesting boats to sail. They probably will be sailing tonight in there. And I used to own one and never caught any weeds on it or plastic bags, an area filled with weeds and plastic bags. So we borrowed some technology there. Here's, I think the day before we left, we took this video. So you can't see too well. How do I get rid of the black box at the bottom? Is it the one on the right? We'll just do that again. That's a little bit better. So we were seeing speeds in the old days were around 2.2, 2.3 knots. We're now at about 2.7, 2.9 knots. So we got a fairly significant speed increase. The downside to this boat, and I'll tell you one more time, is notice the pitching of the boat. It's rather extreme. This is taken in about 8 knots of breeze. You can really see a lot of pitching. And the reason for that is right here, is this V hull. And the V hull has a very gentle motion, but allows large displacements, particularly in pitch. And so we said, that's not so good. The specific reason for this is actually all the batteries are stored in this portion of the hull. And so we were able to get a lower center of gravity. But what we found was the pitching actually slowed the boat more by the added wave generation from the pitching. So the new boat has a much more rounded hull shape. Although the batteries are higher, it tends to pitch a lot less and therefore go faster. So we strengthen the keel. Our keel deflection numbers, over the years, we do a very simple test. We say, how much did the keel deflect? We build it, that was a theoretical number. It started at 9 inches at 90 degrees in air. And what we found with that was it worked on some boats, but loose cannon, really we found out that in certain choppy conditions, you could get a natural frequency response out of that large keel deflection. And you ended up, essentially the bulb was then moving the boat and the whole boat would bounce around. So over the years we've decreased it. We're now at about 2.5 inches. So what we do is we just lay the boat on the side, put the mast in, grab the top of the mast, step on it hard, and the bulb should pop off the ground. And then we measure the deflection of the bulb. And we're using about 2 inches now for that. And in this case it was plywood with 1 layer of unidirectional carbon on the side. So in designing the new boat, we did basically what we've always done before. We have a program called the Velocity Prediction Program. How many people know what that is? Okay, great. The one we use is open code, you might say. It's an Excel spreadsheet. There's a copy of it on our website. You can download it and use it as much as you like, as long as you're not using it for profit. And the numbers in there are for, actually I think they might be for loose cannon now, and so you can have a comparison as you start using it. But basically it's a series of mathematical equations, assuming that they all fall in equilibrium, and you can change parameters of the boat to see which makes the boat faster. This year's group started with Spirit of Annapolis and did studies on beam, boom length versus sail area, displacement, and all these different things to see what would be best. Here's an example of a result. This one is not terribly earth-shattering. These are the number of seconds it takes for the boat to sail in a complete 1 mile circle. So with 15 square feet of sail area, and the way we did this was we averaged the results from 3 wind conditions: 6 knots of wind, 15 knots of wind, and 24 knots of wind. So from those 3 conditions, 15 square feet of sail area, we've got about 1,875 seconds to sail around. And as you increase the sail area, not surprisingly, the boat goes faster. Until a certain point, when, particularly because of the 24 knot wind, that extra sail area is causing you a problem, and you have to decrease the sail area. And the trick with this was changing some rig dynamics to see, okay, if we lowered the mast and lengthened the boom, which lowered the center of effort, could we carry more sail area, which would be better downwind and better in light air? So we varied the mast height and the boom until we got something we wanted, which is, in this case, it tended to bottom out at about 32 square feet for this boat. My apologies about the units. Yeah. All right, you saw this. The basic construction of the boat, pretty simple, but a number of important changes this year. The way we do this is we basically take a block of foam. After the students design it, we put it on a 3-axis mill. Nothing really special there, with a ball cutter on it. And we cut the hull to a thickness of 10 millimeters. And it cuts not only the hull, but it cuts the bulkheads. It's called a ShopBot. The ShopBot cost $10,000 about 15 years ago. And it takes about 4 hours to make a hull. So it's pretty quick. The foam that we use is unfortunately a little bit more expensive than it needed to be. We paid about $400 for the block of foam that this was carved out. We had to pay that much because we're the government, I guess is the answer there. If we had gone out and bought it on Amazon, we could have gotten it for $200, but that's the difference there. One change we made this year was we reduced the density of the foam from 18 pounds down to 10 pounds per cubic foot. Sorry again for the units. But what we found was with Spirit of Annapolis, after we dropped her a few times onto the concrete, she hadn't dented. So we realized that we could reduce the foam density for that. And it's just 1 layer of 4-ounce fiberglass on the outside, so it's very light laminate on there. So waiting to happen was launched. It was a hazy day, actually. She has a very simple layout, and our trademark handles to pick the boat up, and she nicely is quite a bit lighter than Spirit of Annapolis. What we've got here is a partially balanced rig. The mast rotates about here, the leading edge of the mast is here, and it's got what looks like a gaff-style rig on it. And she sailed that one day pretty nicely, but then we decided we were taking off for SailBot in Vancouver the following week, and we decided not to take the new boat, but to use the old boat. So what were the specific changes on that boat? Well, she was 20 pounds. Spirit of Annapolis weighed 118 pounds, and that was just too heavy for 2 people to pick up and carry around. We don't have a crane. So we said, ultimately it needs to be lighter, but then the Velocity Prediction Program also showed us the boat should be lighter for better performance. So she ended up being about 8 kilos lighter. She has a slightly less sail area than the other boat, possibly because the optimization ended up on a lower displacement boat. But she has similar stability. She's a little beamier, but she has a little less ballast. But she ends up across the board about the same stability. She's quite a bit heavier than Gill, almost 80% heavier. So you can see a little bit of the difference between whether the boat should be around the buoys or across the ocean. You need that extra bulk. But one of the key things about this is the volume. The internal volume of the boat is significantly different. It's almost 4 times more volume in the transatlantic boat than in the around the buoys boat. And that's because of, in particular, battery storage needs to be in there. So we looked at the velocity prediction program results, and for those who are at Lubeck, I presented a paper showing the micro-transat type routing for us from Newfoundland over to Ireland. And that was an expected time of about 17 days. Well, with the new boat, that dropped down to 14 days. And that becomes significant because when you start using basic reliability theory, and this is the one equation I put in here, actually, and the paper doesn't even have this. Anyway, it's just very simply, you take the probability of success of each of the system items in the boat. So for instance, the probability of success, and the way we did it was on a global scale. We would sail the boat for an hour, and every hour we would essentially log how many hours we did and how many failures we had, and that would give us a probability of success per hour. We can then extrapolate that out across all the conditions we sail the boat, multiply by the hours, and there's a total probability of success for the voyage. Relatively simple. There are other factors in there in the paper that are discussed, such as hitting icebergs, or whales, or Ireland not in the right spot. And those each have a different probability of success that you would multiply in here. But the idea is pretty straightforward. So from that, and it's mostly because all these things are multiplied by the number of hours, we're able to reduce the probability of, increase the probability of success from 58% to 88%. A number of years ago, my boss said, how high does that number have to be for you to launch and send the boat out? And I said, well, there's actually two factors, not one. One is, that's got to be 90%, is what we decided. At 90%, we're going to go. The second thing is, you've got to give me enough money to get to Newfoundland. And so this year, right toward the end, Matt and I decided that the reliability was probably at 90%. But the bosses said, you could either go to Wales, or you could go to Newfoundland. And so here we go. Wales sounded better than Newfoundland. So a couple other projects we did, not so much I think in the microtransat world, but in the SailBot world, multi-hulls have been experimented with. Queens had one, Waterloo had one, the Royal Military College of Canada had one, and apart from providing lots of entertainment value, they at times would very quickly. And so the question was, could we do one that would not capsize all the time and be high performance? And so what we did was we said, okay, the constraints were it had to be a SailBot, and it couldn't be bigger than that. And that really is, I think, the downfall to the multi-hulls, is they end up being just too small. Because what happened was when you shrink that down, certain aspects of a SailBot, the batteries, for instance, don't get lighter. Whether it's a monohull or a catamaran, you still need a bunch of batteries. Catamarans and trimarans work well when the boat is very low displacement. When you make a heavy catamaran, it just goes slow. So what our students did was they designed, we got two students, one to optimize a catamaran-style SailBot and one to optimize a trimaran-style SailBot. And then we actually did that both in the computer, and then we took some tank testing and duplicated that at certain points in the test matrix. And what we found was, here's the plot. At low speeds, the boats are hardly any different. As the boat speeds pick up, one of the things you notice is that the resistance of the blue one, which is gill the boat, is actually quite a bit less. So if you put that back into the VPP, if you said that the catamarans and gill the boat have the same sail area, for instance, same drive force, gill the boat would win every race. So the trick was then to look to see, okay, could we increase the sail area on the multi-hulls to compensate for that? And the problem was that right at about 8 knots, if you got it sailing in 4 knots of breeze, right at about 8 knots of breeze, the boat just routinely capsized in the model. And so you'd have to change the sail area or come up with a control algorithm that could ease the sheets round up or round down, either way, and respond that quickly. So I asked Matt to write that program, and he basically said, I'm a volunteer, no way. And actually, I don't think it's possible, because anyone who sailed a catamaran knows how difficult it is, as that leeward hull is starting to vary, to get it up and going. So we came to the conclusion that it was probably not feasible, and certainly not for microtransit. The last thing we did that was a really cool project was, originally we said before we cut the keel to try to make this boat faster, let's see if we can just increase the power. So just increasing the sail area aft meant that the boat was going to be out of balance. So then we added a jib and the whole rig rotated, called a ballast rig. It's been around for a number of years, and sure enough, it worked quite well. Once we did all the keel modifications, however, it turns out that it would overpower the boat, and it was a bit more complex, so we've shelved it. What we did see is it worked quite well. The boat pointed a little bit higher. Theoretically, the current draw was less, but we didn't actually see that in our data. As I said, it worked well, and the boat sailed quite well with that. I think Roland's going to talk more about that this afternoon. I'm looking forward to seeing that. All right, so that's the end of the Naval Architect side. And there's Matt looking up one day when, where's the boat going? Classic SailBot. Do you want to flip this, or?
Yeah, I think we can. So I'm Matt Hamlet, graduated in 2009 from Naval Academy. Still do some graduate level work at the Naval Postgraduate School in Monterey while doing my full-time job in DC. So we're going to talk about the improvements we worked on to get us here. So, Spear of Annapolis. Effort in this is to try to find as many commercial off-the-shelf parts we can to put in the boat to integrate together as fast as we can. So naval architects keep pumping out boats, and they expect me to, and then they start saying, oh, we're waiting for it to happen. So up in the top left, this was something unique for this boat. If you take a look at our boat here currently, you'll see the control box is pretty well tethered into the boat by wires. We wanted something that we could just fully remove, and also that was fully waterproof, so in case we had some minor flooding, probably from the system student not closing the hatch properly, that's a disclaimer like that, we don't lose everything because we put everything in one box, or control-wise. So in the top left you can see our Pelican case, and shopping for parts and connections were the kind of the project for that, and getting it all together and not missing a solder. We spoke about the wind sensor and the aft mast already. Helped a lot because our masts can be tall and they tend to catch a lot of ceilings. So we bent a lot of wind sensors. So that's one advantage to that. We also started moving, it's not in this picture, the GPS antenna off that stern quarter and up on that aft mast as well. We use a 3-channel encoder. The third channel is an indexing pin. We've liked that product. It's the ones we've been using. You know, here's the hint. You want to kill the Americans tomorrow, put a lot of water onto their wind sensor. We are working on purchasing and testing out some higher water-resistant sensors, and then other kind of mechanical designs to shed water from that device. Inside the boat is our compass. It's a marine-grade compass. If you need to borrow one, I'm sure there's a bunch of them in the boats in the marina, but we don't recommend that. Lithium-ion batteries. So we wanted to improve our battery life, improve the batteries we use, but we also didn't want to blow up the boat or the lab or cause fires. So we found lithium iron to be one of the best solutions for our situation. It has a higher capacity, but if you short it, I've been told it doesn't explode. So kind of a good safety concern all around, especially with working with water and students. So one of the coolest things and most unique things about our project are these new linear actuators you can see in the bottom right. They're connected, the actuators themselves are in the hull, but they're connected through Morse cables onto the deck. The point of this is to allow for all the controls, and there are no holes in the boat, just like the moops. The rudder shaft, well, unlike the moops, the rudder shaft comes through the boat. Like the moops, there's no hole in the boat. So you can see those mechanisms on the top deck and the aft section. So the linear servos, they're a worm gear. They're electric powered. So why do we like that? Well, you can turn it off, and with the worm gear, it locks the gears in place, so there's no power consumption. So future work will be, when can we just turn the sail off and not worry about it? Maybe we can come back an hour, check to make sure it's okay, and not drain power during that time period. Also, forward voltage monitoring. Actually, yesterday, if you saw a SailBot kind of just going across the water, it's because she lost power. So we like to be able to keep our eye on that. So we have voltage monitors that wirelessly report back sometimes, but just the on-the-deck monitoring helps for when we're in the shop to make sure the batteries are plugged in. Power switches. This is a marine-grade power switch. We like that. You can also see right here is a device that measures if it's dark or light outside to turn on a light at the top of the mast for a possible 24-hour or transatlantic transit. So power management. So I've been given the number of 27 days to do a North Transatlantic prediction, although we said a little shorter
That's a pessimistic
earlier.
number.
This is the, design me a system that will do this. So we're able to essentially calculate our power consumption to be 0.6 amps per hour. So that's powered mainly, partially because I use a Rabbit microprocessor and no full-fledged computer, and then the actuators that can turn off. So that's 400 amp hours total at 12 volts to get across the ocean. So how do I do this? Well, we're going to put some batteries in there, and that gave me 144 amp hours. And now I'm scratching my head, and if you guys would like to join in and scratching my head and help me, that would be awesome. So solar is kind of the first common choice. We weren't given access to the high-tech space grade, really deluxe solar panels, so we bought one from West Marine. It's claimed to be 150 milliamps. We measured it to be 20. So ouch.
But that I should clarify, that was based on 8 hours of onboard testing. And the problem with that is the boat heeling, the sails blanketing, and so on. So that's a pretty representative percentage you might get from mounting a solar panel on deck for a boat.
So fair enough. We figured we could put 6 on, but that wasn't going to meet our needs. So now my project when I go back to the U.S. is try to figure out how to get one of these wind generators to work. It causes a lot of drag, but as we look at going across the Atlantic, we're looking at a downwind run, meaning that drag is in our favor. Anything pushing us to this side of the world is a good thing. So it actually is somewhat feasible. Looking at where the weight is on that and trying to reduce part weights, it's going to be a common part of the project as well. So other sailing performances. So what the Naval Arctics didn't tell you, and I think you guys will understand this, is their new boats don't tack. Does that make sense to many people in this room? So normally when you're sailing downwind and it's a really windy day, you kind of do a chicken jibe where you tack around, you don't have to do that. Well, we actually chicken tack. So since the boat, in that video you saw it just kind of bob up and down, it does that a lot through a tack. So he said, all right, Matt, hey, what happens when we just turn the other way? Okay, we'll give it a shot. This is going to be quick. We're going to be doing the transatlantic in 2 months. This is no problem because a lot of our projects, we try to keep everything similar, and the code base up to that point was similar until we tried to do this jibe thing. The jibe happens, and everything just kind of doesn't work out in the code. Well, really what happened was our jibes were, I'm going to say, lethal enough. Basically, the boat turned so fast that the sensors weren't able to keep up. So this kind of brought us to an idea of, well, when can we trust our sensors? There's a lot of noise, but is there situations where we just simply say, quiet down, let's not pay attention, we're just going to steer a steady course of this for a couple minutes and see what happens. So anytime I say a couple minutes in systems engineering, I get nervous. You don't really ever want to put a fixed time in anything. Well, we did, and we're having okay results. If you're looking at the Atlantic Ocean and is trying to get across, I think it's doable. When we were trying to do SailBot, we actually had to do a lot of tweaking to those times depending on wind conditions, wave conditions, the speed of the boat, what sails we have up, because that kind of matters a lot. But we were able to get the job to work and the boat to sail fairly quickly because one of our goals is, unfortunately, to sail the boat not only across the Atlantic, but with some speed, at least speed compared to the boat. So, every little second counts, especially trying to get onto the other tack. But, alright, so jibing, that's one thing, but what if the wind shift happens? You guys have seen it all week so far. Wind shifts happening, the boat's kind of coming up, bluffing, not sure what to do. So we have that problem with both boats. So, with Gil, we just throw the rudder hard over, and normally she kind of comes out of it. With the newer boats, Spirit of Annapolis, waiting to happen, they just kind of park there, and boy, I tell you what, they sail backwards perfectly. So, I've been in many regattas sailing backwards perfectly. Actually, I've used many starts backwards, apparently, if you guys watched yesterday. So, what could we do there? Well, Sailors are taught to kind of back the boat. It's one of the tricky things. Once you figure out how to go forward, then they say, okay, let's go backwards. So that's essentially what we do with waiting to happen. We realize the situation has occurred. Essentially, the wind sensor has been pointing forward for a while, and we're not really moving. So we back the rudder in such a direction that the boat, it's basically just a full rudder to one direction or the other, that the boat backs until it comes out of that iron situation, then falls off and sails forward some more. Additional research or work is being done to, this won't work for our older or newer generations boats, but the ones with jibs, to be able to back the jib to kind of create that backing moment to do this faster. So kind of two interesting solutions to common problems folks see when sailing. And that kind of concludes our speaking portion. You can see it in the background. It was a kind of rare day to get the first 3 boats out in the water racing along. And that's the conditions that the boats were built for. So I appreciate the sponsors here. And then back in Portugal, we do really enjoy coming out to this side of the world and competing. You guys have done a wonderful job. Questions?
I should point out that in a couple of years, we're going to offer to host the World Robotic Sailing Championship. And unlike this picture, we guarantee there will be wind.
Then we will have enough wind there.
Absolutely.
But for now, let me thank you for a really, really very interesting talk. And I suppose there should be some questions. Oh,
excellent.
What about you guys? So this was not the talk with the sleeping stuff you announced. Oh, it was. Oh, no. Well, I do have 2 though.
Oh, okay.
So the first one would be you mount your wind sensor behind the main sail.
Yeah.
Do you get the real wind?
No.
What do you do about it?
But what you can do is, if you sail the boat in its upwind by manual control, sail the boat in what you feel is the right upwind condition for performance, you measure that wind angle and then you use that as
So you sort of calibrate.
Exactly.
And does it work? Is it linear? I mean, if you have different wind speeds, probably it is not.
It's not linear, but it's close enough. It's close enough. We've tried to sail the boat a little fat, a little aim downwind a little bit more, instead of going on the optimum close haul condition. For Gilda boat, we're off about 3 degrees below that. And for Spirit of Annapolis, I think we're at 7 or 8 degrees below that. Because without the jib, she increases speed a lot more than
Well, second idea or second question, I do like those linear servos, and we looked into that before, but they tend to be pretty heavy, and I know there are some that are IP67. I was just wondering what's the weight of these guys you are using, and are they sealed?
They are, they're sealed, but they don't claim to be waterproof, which is why they're inside the boat. We have different sizes, but they all weigh around 1.5 kilograms.
Oh, okay.
Yeah. Now, the interesting thing is you trade off speed versus throw. And on these waterproof Morris cables, they're actually modified brake cables for your car, the brake system. So they're fairly tried and true, and they're 400 grade stainless, so they don't corrode. The rudder one is short throw, high rate. The sail control is long throw, slow rate. And then to get the sail to actually trim fast, it's a reverse purchase system. And they've been very, very reliable. We've only had 2 failures of the servos. One was a fuse because it was cross-wired, which was operator error, and the other was a bolt falling out. And that was it. Otherwise, they've been very reliable. And they come, Matt can explain it, they come basically ready to plug and play. You don't write a code for them.
Yeah, part of the control for those are these actually 2 green boxes. So all we tell is a pulse width modulated signal like your RC controller has, and it does the power conversion for the motors and all that.
The downside is they're about €150 a piece, but they claim a 10,000 cycle minimum work capacity.
Power generation. Have you think about using ice regeneration with a propeller?
Oh, yes, we did. In our towing tank a few years ago, one of the students did test that, and we went back and looked at the data. For the power we need, the drag is just too much.
Too much.
Yeah, the unfortunate thing about that drag is it's always slowing you down. Whereas with the wind turbine, the drag from the wind turbine, if we're going downwind to Ireland is pushing us forward. Yeah. The downside is, and we're going to have to somehow figure this out, is that added drag will actually heal the boat more. And right now the boat is designed to sail up to 40 knots of breeze. And that will come down a bit with the wind generator on there. The wind generator that we showed is designed for winds up to 50 knots. So it's a voltage regulator controlled so that it starts powering at about 8 knots and will generate power up to about 30 knots of breeze.
So, just one quick question, because I believe now we used up all the extra time already, but Mark already.
Just going back to your 600 milliamps for your Rabbit board, is there nothing you can do in the firmware for that to reduce power consumption?
So that includes the servos. The Rabbit is 200 milliamps. Can I turn it off? I don't. I think it's possible, but we haven't looked
Does it
into
not
that.
have kind of sleep modes and a watchdog timer and things like that?
I believe it has those resources on board, but we haven't explored that yet.
So where's the other 400 milliamps going on this?
Those well,
Actually, yes.
those monster servos,
Yeah.
when they're, or not servo, I guess servo motors
Yeah.
when they run.
So that's your average servo consumption is 400 milliamps.
No, that's our average total boat consumption
I mean,
over.
for the servos though, you said 600.
Oh, yeah, yeah.
Minus the 2.
That's right. I'm sorry. Yeah.
Okay.
That's from I think it's 114 hours of data collection is what we got for our average.
So your algorithm is about not moving the sail so often and stuff like that. That's what's going to save it, isn't it?
Yeah.
That's
That and maybe the wind generator.
Yeah. I hate wind generator.
Yeah. That's why we didn't go there yet.
Well, thank you once more.
Oh, you're welcome.
Question is this.